I am sorry I cannot be there in person. I'm quite envious of you all. But I am here today to talk about the endurance mission concept and um, the current status of this. So, what is endurance? So, endurance is a mission concept that originated in the last planetary science and astrobiology decadal survey. So, that is the process by which NASA and the national academies basically solicits input and devises strategies for uh, large programs at NASA on sort of 10-year, aka decadal timescales. And as part of this process, they prioritize medium and large robotic missions for NASA. And endurance was one of the concepts that was actually developed during this last decadal survey. It didn't exist before 2020, but ended up becoming one of the highest recommendations within the decadal. And in particular, it was identified by the decadal survey as the highest priority new mission for NASA's Lunar Discovery and Exploration Program. And you can see little links here. I'm just pointing out that both the decadal survey and actually the endurance concept study report are both public, and they're massive documents, but you can read them to your heart's content if you want. So what is actually endurance doing? Endurance is a mission to the far side of the moon. And so I love showing this animation from Goddard Space Flight Center showing our familiar near side of the moon, and then we swing over to the lunar far side in a second. And the far side is really important because it just looks so fundamentally different than the near side. And in particular, I mean, we could spend the entire day talking about just this animation, but of most importance is down in the southern part of the lunar far side, you can see the slightly darker region, which is actually the South Pole-Aitken Basin. So I'm going to transition from this animation to a still image, an artificial image that I created, showing the far side of the moon. South Laken doesn't really pop out very obviously in most visible or color images of the far side of the moon, but it just jumps out at you when you look at it in topography. So that's what I'm showing here. South Laken Basin is the largest and oldest undisputed impact basin on the moon. It's over 2,000 kilometers across. It spans from the sort of mid latitudes down to the pole. Um, and we know it's ancient. It is superposed by every other crater and structure on the moon, but we don't know its exact age, which is important. And because of this confluence of parameters, SPA has been highly prioritized basically for 30 years. It's one of the most important places to go on the moon to acquire samples and do in situ science. Why why does this big basin matter so much? I'm a geophysicist by training, so I like to think about the geophysics side of this first. Um, it was formed from an enormous impact. So here's an ISAIL 3D hydrocode simulation of the SPA forming impact. You can see in this model, it formed from a 200-kilometer size, so planetesimal sized object smacking into the moon obliquely. This would have excavated huge amounts of lunar mantle, lower crust, presumably splattering it all over the lunar surface, although it may have been buried and turned over by subsequent impacts and other processes. So it really reshaped the moon. And I like also jumping from the moon to then other planetary bodies. Um, uh, these sort of SPA scale or like mega basin scale impacts really dominate planets and moons and worlds across our solar system. And it's kind of surprising how little we know about their formation process and the details by which these giant impacts affect planetary bodies. And so SPA happens to be the closest and most accessible class of megabasin in the solar system. Now it's also the oldest basin on the moon. So here's a little cartoon diagram of solar system history, in particular the earliest part of solar system history, with the Earth and Moon formation on the far left. Um, and most of the samples we have from the moon, from the Apollo and Luna terrains, are really in the sort of 3.5 and younger billion years old time frame. And there's this missing piece of the geochronology story, which is when SPA happened. So things like whether there was or was not a late heavy bombardment tied to migration of giant planets, that's an outstanding question. All these impacts are happening at the same time that life is first emerging on Earth. So understanding what the impact flux and nature is in this time period is important for sort of understanding that emergence of life. And all these terrains are otherwise lost on other planetary bodies. So the oldest rocks, whole rocks on Earth, for example, are only about 4 billion years. And SPA is firmly in this ancient terrain. So it's an undiscovered country in terms of time. So all this isn't new. SPA has been prioritized for a long time. But there have been challenges with trying to accomplish SPA science using traditional mission concepts. And so here's that same view of the moon. On the left, I'm actually showing the specific objectives that were developed in the endurance concept study. They look vaguely like objectives for previous South Pole-Aitken Basin mission concepts. They include things like determining age and looking for volcanic terrains. But the problem with SPA is it's so big and so geologically diverse, it's hard to go to a single spot to confidently address all these objectives. So, for example, if you wanted to date SPA itself, one place you might imagine going is to the impact melt sheet in the center of the basin, or the compositional anomaly in the center of the basin, often called SPACA, shown here in green. So that's one location. Now, if you want to test late heavy bombardment, then you actually want to go to the other superposing impact basins in SPA, shown here in the cyan color. If you want to look for mantle material, which is, I'm showing one particular example of places where folks have speculated that you might find mantle material traced by high thorium anomalies. That is yet a different location. Volcanic terrains, another location. And so you can see it's hard, if not impossible, to find a specific location where you know you're going to get all the types of material that you need to answer all these objectives. You might get some of them, but to really know you're going to answer the questions, you need mobility to get you around to acquire a large amount of material. And that's where endurance comes in. So endurance here is a little sketch of our traverse. So this is a large rover concept, and it would drive 2,000 kilometers from the center of the basin down to the South Pole where it would rendezvous with Artemis and deliver its samples. To give you a sense of scale here, for those of you who've traveled around the United States, the Washington Mall is about the size of typical early Artemis EVAs, even with unpressurized rovers. It's also roughly the scale of some small rovers, robotic rovers you could imagine sending. Endurance is like driving from DC halfway across the United States to Chicago through the Appalachian Mountains on a weird path. So it's just a vastly different scale than we're used to thinking. In the concept, we developed a baseline concept that had a huge number of instruments, of something like 10 instruments. These are actually adapted from a previous concept study called Intrepid, which was another marvelous long-range rover concept that really changed the paradigm in the decadal. But you can see this is a pretty large rover. These wheels are about the same size as the Apollo lunar rover wheels, so that gives you a sense of scale. And the big deal with this rover is its mobility system. To do 2,000 kilometers, you have to drive very fast by rover standards. So a top speed of 1 kilometer per hour, which is, it's hard to drive that slow in a car, but that's very fast by a rover. And you need to be able to do that autonomously, both in day and night, in order to accomplish the mission in a reasonable amount of time. There's all sorts of fun details about the rover that I'm not going to get into, but we can talk about if people have questions. To give you a sense of what this concept involved, here's sort of a snapshot of the Schrodinger basin, which happened to be on the original traverse. You can see we planned out an actual traverse, going to some pre-planned sample sites. We would stop at 12 sites, grab a large amount of samples from each. And what is, I think, particularly exciting is the opportunity on such a long traverse for all the in situ science you could imagine doing along the way to provide geologic context in a way we've never done. So in the original concept, we actually had almost innumerable stops between sample sites where we would collect in situ data with remote sensing instruments. And again, these are all concept instruments at this stage, and even the concept of operations is notional. But I think this is the kind of stuff to get excited about and start thinking about now. The samples are, of course, the star of the show. Um, and importantly, since we are a large rover and rendezvousing with Artemis, which has a large up mass capability, although that exact number will be refined in the coming years, we have the capability of returning something like delivering 100 kilograms of material to Artemis Space Camp, which is comparable to some of the later Apollo missions. So this is sort of, again, we're doing an order of magnitude more distance, but we're also doing an order of magnitude or more from traditional robotic sample return missions. Finally, what's the path forward for Endurance? So this is a little timeline showing basically the life of Endurance so far. So it originated in the decadal. We're now past the decadal, and since then there have been a lot of follow-up work, both with the community science workshop that we had in Pasadena, and an ongoing study at JPL to refine the technical side of the concept. But the biggest thing for this community to be aware of is that NASA is planning to initiate a South Pole-Aitken Basin sample return exploration, or SPARCS SDT, which is effectively defining the requirements for endurance or an endurance-like mission. Now, once this happens, it's still a long road past that before this mission ever gets fully confirmed and developed and flies to the moon. We're thinking this is something that would happen in the early 2030s. And with that, I will stop since I think I'm out of time, but I will leave up my slides. And again, just remind people to pay attention, especially with the SCT coming out. NASA has indicated that there may be opportunities for international participants on the SDT. So thank you very much.
Thank you, James. I don't know if you could hear that. You got an enthusiastic round of applause. That's a really interesting chat and perfectly to time as well. So I've got a couple of minutes for questions if there's any questions for James. If not, I'm quite interested. I mean, that's really incredible. And the amount of samples that you'd be accessing. What are some of the challenges around perhaps cross-contamination control with this kind of robotic approach?
That is a great question, and actually, it's on my long list of things that I think the SET will have to think carefully about. In the original concept, the rover basically just had 12 open boxes on the side of the rover to collect rocks and regolith, and there was not a strong constraint on cross-contamination between sample boxes, basically because everyone kind of expects the moon to be mixed to some extent laterally anyway. But that's sort of a great example of something very specific that immediately has technical implications for designing and costing a rover. At the end of the day, I kind of suspect the ultimate constraint will actually be driven from the human exploration side of things, making sure that these boxes, the sample containers can be removed, appropriately sealed so that way they don't pose a risk to astronauts on the journey home. But that's something that the SCT will really need to work out.
Great, thank you. Are there any other questions in the room?
Yeah. Ben Greenhagen, APL. So James, this is somewhat of a related question. You mentioned potentially 100 kilograms of return sample mass. Is that looking towards what Artemis might be able to provide, or is that really being constrained by the rover's capabilities of bringing back mass? I'm envisioning a scenario where maybe you could bring back even more materials than the Artemis return could allow for, but then you could do some high grading by the astronauts.
Yeah, that's a great question. So, I mean, I'll tell you the actual origin of the 100 kilograms number is early on in the development of the concept, we were like, we want a number that pushes the engineers. And we knew that that number was roughly commensurate with expectations for early Artemis missions as well. Like Artemis 3 has a total up mass, including theoretically a mass of that range. Um, and you don't want to go too much lower, like you don't want to go in the 10 kilogram range or so, because then you start running into science challenges like statistics of samples. So the 100 kilograms was a nice push. It turns out that there's also from the engineering side, it's a nice sweet spot in the technical design of the rover. This class of rover can easily carry up to 100 kilograms. It could carry more, but if you go too much more, then you start having to redesign the mobility system, and you end up building a bigger, aka more expensive rover. And so it's at a nice little sweet spot right now. But there are all sorts of clever solutions I can imagine one employing for actually getting those samples from the surface of the moon back to Earth, as you said, either multiple missions, if you have different capabilities with Artemis or on different missions, or even in situ instruments that could analyze some of the stuff on the surface. There's all sorts of fun games that I could imagine playing, and hopefully that's something that we all can think about in the next few years.